our colloquium. Today it's my honor to have Professor George Ho to give his recent, it's not theory, his ideas. Before the giving this talk, I would like to give a very brief introduction. Professor Ho is our alumni. He graduated in 1980s, obtaining his bachelor degree. Afterwards, he went to UCLA to get his PhD. Then he spent his research years in the in Pittsburgh, University of Pittsburgh, and the Max Planck Institute in Munich, and then PSI in Switzerland. So in 1992, he went back to NTU as at that time he was an associate professor. He has received very many actually awards. I think to me the most shining achievement from George is he established the high energy experimental group at NTU, and we regard him as a theorist, also an experimentalist, and he is now the chair professor in our department. He also received the national chair in the MOE, it's Ministry of Education, and he was awarded the ABS Fellow last year. Okay. And today he's going to talk about the Decadal mission for the new Higgs flavor era. Okay, let's welcome Professor Ho.
First let me thank our chairman, department chairman, and also chairing this session, Professor Chang, for actually inviting me. So when he asked me first time during summer, my first response was that actually I have given a colloquium a year and a half ago, so I felt that was a little bit too close. But since I'm still passionate on this whole subject, and since I guess the chairman, I thank him for his grace. I think he took it into account. So I hope I do somewhat better this time. And I thank a lot of senior professors to come. I'm very grateful. So any astronomers here? No. But this decadal mission would echo with astro people. Okay, this is a colloquium, so I would first say that it's pretty small print. Not everything I say would be highly precise. It's unavoidable, so forgive me. So we're in this building where the physics department and I guess condensed matter science center people are probably mostly not here. And next door we have this fancy Cosmo building. Well, in a certain sense, I'll be touching on all three, but it's basically a particle physics talk. Okay. Now, I use the word error. Physics is experimental science. Okay, so we necessarily mean there's ongoing experimentation. Otherwise, we're not in an error. Okay. So the new, and here I switch flavor and Higgs because NTU, when I initiated the particle physics group, experimental group, we started with Bell, and this is now the second generation Bell experiment. This very successful experiment at LHC called LHCb, so these are the flavor experiments. Our group is also in this CMS, compact muon solenoid. So compact, if you look carefully, now I understand, I can walk around. If you look carefully, up here there are railings, ladders, and so on. So this is a huge detector. And Atlas is even larger. So that's the modern day particle physics experiment. So this is the outline. I'll start with a prelude on dynamics, mass, flavor, and universe, each using a key symbol, key concept, etc. to illustrate. I'll try to bring forth to you the standard model, the Higgs mechanism for mass generation, and so on. Now, this is just to entice you. Totalitarian principle, whatever that means, and I'll bring out the second Higgs in the main part of the talk, the content, if you want. So this is like a long introduction of where I want to get to. But if you look at the color coding here, it's all about the Higgs. What about the Higgs sector? And the Higgs is deeply intertwined with flavor. So I'll talk about big issues, and so maybe I'll turn the thing off. No, I don't. Okay, doesn't matter, do the same. So here I have the research topics, and then I'll define clearly the Decadal mission. Okay, so let's start from our common heritage. So, of course, electron was discovered by J.J. Thomson, radioactivity, Becquerel, and Ernest Rutherford picked it up. So our common heritage is that he saw through and saw the nucleus of the atom. So you know that. But Rutherford was the guy to not only understand and also give the name alpha. He understood before he understood there was a nucleus, that alpha is the helium doubly charged ion. Beta is radiating the beloved electron, and gamma, you know the symbol, okay? So, so here on this page I have two other comments. We will be bringing in the weak interaction. In a sense, it was already known to Rutherford, and this is not only modern, but this is the way it is. In fact, it's a neutron most of the time, decaying to a proton with an electron and an electron neutrino. It's called a full Fermi interaction because you know for sure electron, proton, neutron are fermions. So that shows that this guy here, neutrino, is a fermion. So it's called a full Fermi interaction. That's the weak interaction. Well, on the lower left corner, Camelin onus, superconductivity, what does that have to do with it? Well, one thing that's connected is that it was discovered in 1911. And it will illustrate a very important concept as we go on. Okay. So along the path of Rutherford, it was actually Rutherford who not only, of course, it's easy to see once you know the nucleus, that the proton is helium plus, not helium, hydrogen plus, the ion, okay? But he was the guy who demonstrated that protons pre-existed inside the nucleus. He even anticipated the neutron, okay? So following the path of Rutherford, as I'll illustrate, we discovered quarks. So this you should know by common knowledge, that inside the proton there's a UUD, and the up-type quark is charged 2/3, down-type quark is -1/3. So if you do the math, proton is UUD, is charged +1. Neutron is UDD and is charged neutral. So this is the fundamental constituent of U, okay? The interesting thing, I put a question mark here because up till this day, let's say if the quarks were discovered around 1969, to this day, we know of no structure of these objects, okay? The age-old electron. And so the word elementary or fundamental means structureless in particle physics, and that's what particle physics is about, okay? So at this stage, let me challenge you. Do you know why is the electric charge real? Okay. Now, by this I mean that we all know since childhood, you say, that same charge repel and opposite charge attract. But what if the concept of charge or coupling is complex? That doesn't work anymore. So think about it, okay? Why is it real? Secondly, although the coupling constant enters, but atomic size is practically determined by the electron mass. Okay, so hydrogen atom is the Compton wavelength of that of the electron divided by alpha. Okay, so but who decides? Who determines what gives the electron its mass? Very fundamental question. Don't forget, it's a point-like object. It has no structure that we know of. So with this, if that's difficult enough, by 1937, we knew the existence of this muon. And quickly we knew its mass is about 200 times electron mass. And then we learned that it's just something extra. So Rabi, had this famous quote. You argued that. Well, the story is that Rabi was the that way. Can't hear you. So it is said that Rabi was the first Jewish physics professor at Columbia. You would not have guessed, okay? And you know that Jewish people, especially in New York, they like to go to Chinese restaurants. So that's the context of who ordered that. Who ordered that dish, you know? Because it's very heavy flavor. So I'm going to introduce heavy flavor. So the muon problem, the problem articulated by Rabi got worse. Now we have 3 copies. Now at the time of Rabi's quip, we knew of strangeness, turned out to be the strange quark. But then if you jump in time, 1974, Sam Ting found his charm quark, and shortly thereafter, the tau lepton, the B quark. But it took another 2 decades for the top quark to be seen. Okay. Okay. Now the problem. So I'm not going to talk about neutrinos, the beloved subject of Professor Schoen sitting there. You see that it's really in a separate group. Now this is a log plot. So here there are actually 2 orders of magnitude. But I have an old joke for old-timers. The problem with a log plot is that if you put, listen carefully, Sophia Loren on a log plot, she will look pretty flat. Okay? So let's get into a linear plot. It's astonishing how broad range these masses are, okay, that a log plot fails to exemplify. The electron is 0.511 MeV over c squared. The top quark is up, that ceiling is 173 GeV, okay, it's 10 to the 6 times larger. So we have a problem with mass. Where does mass come from? Didn't I say who decides on the electron mass? Now the problem is really much more complex. Okay, in the previous slide you saw positron. Now we actually knew about the positron before the muon, so Anderson. Positron was actually named by him. It's an anti-electron, an electron that has opposite charge to the electron. It's easy to see in this plot. So I guess the magnetic field is going into, so this is a photograph of a Wilson chamber, a cloud chamber. So you have a cosmic ray entering. so it's bending because you have a magnet. And you put a lead plate, you absorb some energy, so this is a slower electron, it bends more, okay? So if you do this experimentation, you can learn what is going on. So this brings in a third question. Where has the positron gone? Now the positron is very light, so it's actually easy to produce. What is not easy are baryons. What is even more difficult is nuclei. So it is said that if one sees one single anti-carbon, it will be proof that anti-galaxies exist. But we haven't seen one. We also don't see any abundance of anti-baryons floating around us. So this should really be said as, where have the anti-baryons gone? Now you all know about Big Bang. Big Bang should have produced matter and antimatter equally. So we have a very big problem called the baryon asymmetry of universe, BAU in short. So on the right-hand side I have the muon. In fact, it was also discovered by Anderson and confirmed by these people. And the mass was known. Now, for this talk, I was happy to dig out for myself this paper by Pontecorvo, a very famous name in neutrino physics. So he did the first experiment to show that the muon does not seem to decay into electron plus a photon. That is the no-brainer, okay? Because, okay, this also shows that the muon is not an excited electron, okay? It's exclusion, if you want. So this is the context, I think, about this time that Rabi said, who ordered that? Who ordered the muon? Why do we have it, okay? And this is the period, 1932 to 1947-48 is about the time where the birth of particle physics, okay? So for particle physics, I have a few other things to bring in. One thing is CP violation. It's related to baryogenesis called the Sakharov conditions. The backdrop is what all Chinese would know, parity violation, 宇称不守恒, okay? So it was conjectured by Li and Yang and Li, and quickly confirmed by Madame Wu in 1956. So since physicists, especially particle physicists, love symmetries, so for a long time, well, not so long, for almost a decade, particle physicists thought that the product symmetry, C times P, P is parity, space flip, okay? C is charge conjugation, you flip particle to antiparticle. So it was perceived that this would be a symmetry of nature. But this paper, I would not explain it, only 4 authors, and they proved that CP is violated in nature. And these 2 guys who I show, Cronin and Fitch, received the Nobel Prize in 1980. Okay, so now what does this have to do, or how did Sakharov enter? You may or may not know, it's written down here. Sakharov is the father of the Soviet H-bomb. I think after the war he was absorbed into the bomb program in the USSR. I think in 1963 he was part of the effort from the Soviet side. So US, UK, and USSR signed a partial test ban. Okay. So the backdrop is there was a few years where the Soviet team, all brilliant physicists, well, not necessarily physicists, had some time to do science. So he saw this paper, and then the other famous thing is CMB, cosmic microwave background, okay? So with this, he wrote a very simple paper saying that CP violation can explain, well, not CP, that baryon asymmetry of universe needs CP violation, and his own input is baryon number violation, okay? And I would say as a worker, progenitor of the H-bomb program in the Soviet Union, nobody understands better than him about out of equilibrium. Okay. You may have noticed I'm mostly showing Nobel laureate pictures. So this is also Nobel laureate, but not the one that you think of. He got the Peace Prize. So starting with the test ban treaty, he became a human rights activist and so on. A very remarkable person. I would recommend that you try to know about him. Okay.
George, what's the small u there?
What?
Small u. And
CP
parentheses.
validation and DAU bracket small and u. The Sakharov.
No. Before Sakharov.
That's before Sakharov.
What is before Sakharov?
The second
Yeah.
box.
The bracket.
Oh.
And
It's a
u.
U.
Okay, I can't see it. What are you pointing to here? What bracket?
This
bracket.
Oh, this one here.
No.
The first
In
one.
the title.
BAU. After BAU.
BAU.
In the middle of the screen.
Oh, just read it. And you, Xiaogang. You and him, he.
See? You need to
So it was not a planned question, but I thought you would just read and then. So when you asked me, I completely forgot this planted little thing there. Okay, meaning that okay, this is at the start, still at the start of the talk, so people are probably not yet asleep. But you could have been saying, okay, wake up, CP violation. You say, who cares, right? I'm in condensed matter physics, this and that. But CP violation, Bernoulli central universe, and you, Mr. He, it matters to you too. Thank you, I forgot about this thing. Okay, so CP violation is related to you because baryogenesis is a huge problem. Okay. Back on Earth, and of course for the universe, it's the weak interactions I want to comment a little bit on. So this is straightforward, but by the 1960s, this was the perception of how the weak interaction proceeds. You see, by that time we knew about quarks, so it's a D quark turning into a U quark and doing this radiation. The thing is, the muon decay goes through the same process. So people start to understand that behind there's a bigger gauge group called SU2 cross U1. This is another billion gauge group. I will not fully explain it here, but there's something called spontaneous symmetry breaking that results in only one unbroken symmetry. That's the EM that we know of. So there's a weak coupling constant and our electromagnetic coupling constant. Now, again, in the late 60s at Stanford, people built machines to have 20 GeV electrons, okay? So if you scatter a 20 GeV electron, just look at the microscope concept. The resolution let mankind see inside the proton and found there are massless point-like objects. Feynman called it parton, but this was the quark of Gell-Mann and Zweig. Okay? But besides bringing this knowledge, the point I'm making here is that all this time we find the photon is effectively massless. Whereas the vector bosons here, by that time it was known, they weigh 80 or 90 GeV. So what is this? What is this? And actually, massive vector bosons in the 60s was still a very difficult problem. Even Li and Yang could not handle them, the theory part. Okay, so this introduces massive vector bosons, and this brings us to superconductivity, okay, the Meissner effect. So everybody knows about the Meissner effect. This is one of the few pictures who did not get a Nobel Prize, okay? So this magnet levitation you're familiar with. So this is a superconductor. So I point out to you, this is very modern, ITC. This is a high temperature superconductor here. So what is happening is that magnetic fields cannot penetrate a magnet, okay? Cannot penetrate inside the superconductor. So I don't know whether you remember your London theory. So there's attenuation, but this attenuation is not, it's a form of damping, but what is this damping? The damping is that, yeah, the magnetic field gets damped, there's a length scale, but it's effectively, the photon becomes massive. So this is now familiar across the board in physics. It's called the Higgs mechanism. So a gauge boson turns massive through some phenomena. So this Higgs mechanism was introduced into particle physics in 1964, but the person behind it, the person who saw through it, is Phil Anderson, who passed away half a year ago. So here I show a picture. Yeah, these two are Nobel laureates. So Haldane was his student, but still is. So he received the prize in 2016. So this is a lucky advisor-student pair because Haldane got his PhD a year after Anderson's prize. And Anderson lived long enough to share the joy of his student getting a prize. You love to be one of them, okay? So I use this slide to illustrate how we can have massive vector bosons that started out with massless gauge bosons, like the photon, okay? So this is the Higgs mechanism. Okay, so I'm changing, now I'm moving on to our Higgs mechanism, our standard model, mass generation, and so on. So you saw that my picture taken with God. And I'll not explain further, except these two guys received the Nobel Prize in 2013. Okay. So why do I say my picture taken with quote-unquote God? Okay. The thing is, the God particle was discovered by CMS and Atlas in 2012. If it's the God particle, then the guy must be God, or something like that. Okay, so what we know is that this Higgs particle, the God particle, why is it called the God particle? Actually, it was called the goddamn particle, but why is it called the God particle? People say because it's the origin of mass. The origin of masses of this yellow box. Photons and gluon are massless. Neutrinos are extremely light, and we're not talking about them. So this is the origin of mass, the question that we raised, okay? And we've illustrated, so I'll add a little bit more words. The thing is, this fundamental doublet, why is it a doublet? Because here you see these are doublets, okay? There's a doublet out there under weak interactions. This neutral, charge neutral component develops a vacuum expectation value, okay? This expectation value is non-zero. Symmetry is spontaneously broken because it's a direction selected. The value is V, here on the right-hand side is V. Now, a complex doublet has 4 components. So one component is left over. Okay, here I'll just use descriptive physics. There are 3 Goldstone bosons, as illustrated by the G. Plus means there's a minus. And the Higgs mechanism says that the Goldstone bosons get eaten by the respective gauge boson. So the G plus become the longitudinal component of the W plus, and G0 goes into Z0. And this is the origin of their mass. Okay, Higgs mechanism. Just like superconductivity, photon becomes massive. Okay. So this was understood in the 60s. And photon and gluon remain massless. But somewhat surprisingly, the fermions get mass through a very similar formula. So the answer to my initial question is that electron mass and all the masses we know of, fundamental ones, are dynamic. Okay? Gauge boson mass, fermionic mass, even the Higgs boson itself, the mass is dynamic. There's a scale parameter, this vacuum excitation value. And the truly troubling thing, as we said in the outset, is that fermion mass spans 6 orders of magnitude. What does that mean? It means, the coupling constants, damn it, spans 6 orders of magnitude. So you say, Professor Ho, what kind of a theory is that? I agree with you. But we have measured them. Okay. So these Yukawa couplings, theoretical before, we have measured since 2015 that the W and Z, we have measured the coupling to W and Z of the Higgs boson. We have measured the coupling of the top and bottom and tau in 2018 to the Higgs boson. And this year, we have 3 sigma evidence that the muon does couple rightly with the Higgs boson. So we cannot take this lightly. This is experiment. We know it, okay? So we've already seen this. So let me introduce the Higgs potential. The problem with the Higgs potential is that it's such a nuisance that it's so simple, okay? It's just like this. We call it the 5-4 theory, so there's a mass term, there's a coupling term. The only point is that the mass term is negative. So what happens is that, now, lambda is positive, so you have a wall here for large field. You would think that when phi goes to 0, the potential I put in quotes because it's not exactly all potential, but it's also not, okay? So the potential looks like 0 up here. But because of this negative nature, there's a lower energy out here, and this is the symmetry breaking. The V is some direction, you just pick it, and there's a large value of the field staying there. That is the vacuum. That is the vacuum that we live in. So this such a simple, called Goldstone potential, explains this SSB. Okay. I hope you know what SB stands for. Okay, so if you want to learn more, go to the 2013 Nobel Prize. Now that may have been Nambu's prize. There's still some remarks I need to make on the standard model. So I raised the question, why is the electric coupling real? Let me say we understand why it's real, but I'm not going to tell you unless you ask, okay? We also understand the weak coupling G is real, but complex dynamics does exist, okay? Now you will complain to me now saying, Professor Ho, this is out of my box, okay? Let me explain it a little bit. Now from electrodynamics, Maxwell equation, you know that when charge accelerates, it radiates, okay? So this is a fundamental electron, it bends. When it bends, it's accelerating. So a photon gets emitted to balance everything. So this is not different. There's a Jth type, J can be 1, 2, 3, okay? Down quark. Now bends into an ith type U quark, so that's descriptive. And since the down quark is charged minus 1/3, U quark is plus 2/3, so you emit a gauge boson. This is weak interactions, and the weak boson has charge, therefore. But because there are indices, Ij, there's this matrix, Vij. So you say, oh, he's getting out of bounds for me. Well, this is related to this Yukawa couplings that we started to allude to, okay? So the longitudinal component brings this in, and this is how the Vij is picked up. I will not go into that formalism. The formalism in the end, for the 3x3 nature, was due to these two gentlemen, okay? And this is where the complexity lies. This is a complex coupling, okay? So it's in the 1-3-3-1 sector, and this is experimentally affirmed. So they received the Nobel Prize in 2008 by Bell and Barbar's measurement in 2001. So Wolfenstein parameterization, I'll come back to soon. The comment here to make is that, in fact, you would need all 3 generations, because if you look at the 2x2 matrix, there's no complexity. So the complex dynamics needs 3 generations. Okay, that's the discovery of Kobayashi and Masukawa. But to one's astonishment is that we have experimentally affirmed this matrix. It's all measured. But this CP violating phase, this eta here, okay, falls at least 10 billion times short of producing a Bernoulli symmetry of the universe. So it's very astonishing. CP violation on Earth does not reach the heavens. Okay, so that's the point. Oh, okay. So any questions so far? Okay. Well, a month or two ago, well, almost 2 months ago, one day I was checking something like everything that is not forbidden is allowed. Okay. And these are the first two entries coming out from Wiki for me. So the first one is kind of familiar. and even Germany is mentioned because in Germany you would like to say, das ist verboten, okay? So whatever is not forbidden, forbidden is verboten. So the German law concept is that you have to articulate by law what is not allowed. If it's not allowed, it's allowed. So that's a constitutional type of democracy, okay? But to my surprise, the second entry is called the totalitarian principle that I use up here, okay? How audacious. Everything not forbidden is compulsory. And reading on, it was sourced to this famous man, Gelman, okay? He's a pretty nasty type. You don't want to deal with him, but he passed away, so. So this is what he said. Anything that is not compulsory is forbidden. Okay, let's not enter a linguistic debate. What does this all really mean? But I'll use this, and I show his picture. So he got the Nobel Prize by himself. You know, he's a bigger guy, okay? So this totalitarian principle says everything that is not forbidden is compulsory. If I take that as a principle, not my principle, Wiki says so, okay? We have one Higgs doublet. I've shown you on previous pages. We have one. There's nothing to forbid a second. So there must be a second doublet, okay? Now, we have done symmetry breaking. So the second doublet does not have to generate the VEV. Actually, I should not generate the VEV in a certain concept because it will mess up. So therefore, there are four scalar bosons called the H is a CP even scalar. This I says this A is a CP odd scalar, a pseudoscalar, and a charge scalar. Charge scalar has two components, H plus and H minus, okay? Okay, so it's compulsory, but where are they? And do they do anything? Where are they? Who are they? What do they do? Okay, so that's the theme of the talk. Okay, so I've introduced the totalitarian principle. Now I'm going to illustrate twice that the totalitarian principle is actually very common. This is how Steven Weinberg got his Nobel Prize by this paper. Okay. So his motivation was, so this is a few years after the Higgs paper. So he was the guy who introduced this Higgs doublet to do the symmetry breaking that we have been illustrating. And then, therefore, the gauge boson mass is generated, as we have illustrated. But, you know, I would not call it the totalitarian principle, but in field theory, Lagrangian field theory, the usual statement is, whatever is not forbidden by symmetry, you put it in. Okay? That's a form of this totalitarian principle. So you have a doublet, phi. You have doublet, L. This is just neutrino and electron. So this forms a singlet. This right-hand electron is a singlet. Okay, just take my word. So this is a Lagrangian term allowed. So I used to say that Steven Weinberg is a good student. So good student, when he does the homework, he'll do everything that is required, okay? So he didn't have to do this, but he dutifully put in this term. And lo and behold, he didn't use the word, but that's our Yukawa coupling. Why is it called the Yukawa coupling? Because this is a fermion boson. And Yukawa was proton, neutron, pion, okay? Fermion boson. But with phi having a VEV, that's how we have shown that the fermion mass, electron mass, here is the theory of electron, how the electron got its mass, okay? So, totalitarian principle. And then we found there are actually 3 copies of electrons, 3 copies of down-type quarks, 3 copies of up-type quarks. So that's simple and easy. You enlarge this parameter to be a matrix, 3 by 3 matrix. And the trade is to diagonalize this matrix, and we get the eigenvalues. Those are the masses that we see, okay? So the leptons, there are 3, E mu tau. Down-type quarks, there are 3, DSB. U-type quarks, there are 3, U, C, and T. I've shown them, okay? Now, what I have called the totalitarian principle is that there must be a second Higgs. But if there's a second Higgs, and since nothing stops you from writing this, there must be something like this. 3 new 3 by 3 matrices. And whatever you do to diagonalize on this side, you operate on them, and I'll call that the row matrix. So these are brand new Yukawa matrices due to the existence of this second Higgs doublet, okay? So I've used now from the discovery of the Higgs boson in 2012, we complete a doublet, it exists. We need a second doublet, and actually the backward thing, Yukawa coupling. So we have 3 iterations of the totalitarian principle. And then I say overkill. I'll not elaborate too strongly, but by kill I mean the word, okay? The problem is that when you do this diagonalization, you cannot diagonalize this, okay? It's in general non-diagonal, and because we saw that it's the Yukawa couplings. Oh, by the way, this is the source of the complexity. It's due to this Hermitian conjugate. If this is a matrix, these will be in general matrix complex. Okay, it's fully allowed. Whatever is allowed, or whatever is not forbidden, is not only allowed but compulsory. So it's non-diagonal and complex. This drew great fear from Sheldon Glashow. Glashow was a classmate of C. Weinberg in Bronx High. Okay, and certainly Glashow was a very famous physicist, made many contributions. In fact, this gauge group was proposed by him in the early 60s, okay? So they did not write many papers together. Glashow, I believe, talked to Weinberg, and they wrote a paper, proposed this natural flavor conservation, because having non-diagonal couplings means flavor-changing neutral Higgs. So one of the great works of Glashow is to counter flavor-changing effects. So basically, they just killed. They say, away with them, okay? And now usually people do that by a Z2 symmetry. I'll not go into that. It's automatic in supersymmetry. So I was an adherent for a long time, very popular. But let's call a spade a spade. This was an edict. Let them be all killed. Okay? Remove them. Remove them from my sight. So that's, if not totalitarian, it's authoritarian. Different, okay? In plainer terms, ad hoc. It's just for the purpose of removing them, okay? Actually, in this sense, if we found supersymmetry, that's not ad hoc. There's an a priori reason why we have this, okay? But we have not seen supersymmetry. So we cannot activate that argument. So if you follow the totalitarian principle, who comes from someone more senior, in a sense more achieved than them, then we have to accept this. All this line of totalitarianism you have to follow. Furthermore, this was 1977 that they wrote the paper. This 1/10 of what we know of the top, this is about a factor of 12.5, is about the limit of imagination back in 1977. So nobody foresaw that the top will be 173 GeV, So the top mass, and actually the Yukawa coupling of top is just about 1. It's miraculous. So this is called the fermion mass hierarchy. They did not know. They did not know the red part, okay? What they really did not know is the so-called mixing hierarchy. I did not make very clear, but these are the 3 angles, if you want, of the 3x3 mixing matrix in the weak interactions, okay? There was a very strange, impressive hierarchical structure discovered in 1983, okay? So this is called the quark mixing hierarchy, and they seem to echo each other. This is coming from diagonalizing mass matrices, so that they are connected seems reasonable. I want to convey to students, why do I mention Wolfenstein's parameterization again? So with this, Wolfenstein in that year wrote this paper. I remember my junior advisor, amateur Sony, one day handed me the paper and said, okay, look at this, what is your comment? So the next day, maybe, I came back and said, what's the fuss? What's the big deal? It's only a parameterization. And he said, so why didn't you write it? Okay. I hope you find out what that means. So there's much to be said, but I will not go into it. A few years later, Cheng and Scher made an observation saying that if the off-diagonal behavior echoes this behavior, then the FCNH, the flavor change problem, may not be that big, okay? And then another few years later, noticing that paper, I wrote this, saying that then the largest off-diagonal coupling, in fact, is the top charge, actually covered. And therefore, it's the top decay that's most important. Professor Xiaogang He has already left, but he, for one, did not know I put down the word Model 3. So I generalized not just Cheng Scher, but I said it's really just a mass and mixing hierarchy, correlation. Nobody refers to me by Model 3. Everybody knows Model 3, but I'm not a citation chaser. Up here I say it's an experimental question. Experiment is king. So this is just to show you that in 2012 we found the Higgs, okay? And then by 2014, experiments push below percent. You know, Jack Kaifeng and I and others proudly announced that in 2013 that this decay can be at percent level. And by now it's pushed down to the per mil level. It's still ongoing. Our group, actually Kaifeng himself, is working on this. Another mode. Okay, time is running out, so I'll not mention it, but just say that this H decaying to tau mu, to leptons, was also searched for. Therefore, I think the NFC, the actual Weinberg issue is moot now because experimentalists are searching. The search says these flavor changing couplings of the Higgs boson is an important subject. Okay. Okay, I guess how much time should I go on with? I've finished the introduction. No, it's only 10 pages left. Okay. Okay, I guess the heaven and earth stuff should be interesting. So let me recite, O Lord, our Lord, how majestic is thy name in all the earth, who have set thy splendor above the heaven. The chairman is a Christian, so I guess he'll give me 5 minutes more. This is the Psalm of David. Now, before David became king, in his youth he was a shepherd. So in the dry land called Judea, he had all the nights on night shift to watch the stars. So he has deep insight on that. So by heaven, I mean barogenesis. And down on earth, I would mention the electron EDM. My true subject is the Higgs spectrum and nature's design. We'll try to be fast on that. So this is a slide in the APS April virtual meeting. So I say that the tension, because we need barogenesis, we need extra CP violation for barogenesis, but we see no new physics at LHC. And then interestingly, on Earth, there's a totally different kind of experiment. So Cornell is Eric Cornell. He's a Nobel laureate, BEC. This is Gerald Gabriels. He will get a Nobel and turn black and white if he observes the electron-electric dipole moment. Okay. So I wrote this paper, published this year, on how to accommodate this. So let me give you that story. This rho T is the diagonal coupling of the extra Higgs boson. It's complex. Now we already know lambda T, that's the top Yukawa coupling, is 1. And we have all the reason to believe, if you allow me to use that word, that the rho T itself should be order 1, and therefore it's the imaginary part. So it can drive, so let me not explain this figure now, it can drive electroweak barogenesis very robustly. Oops. So in that paper, 2.5 years ago, we said ACME 14 was already known at that time. This was the bound. And we said this region can still exist if we invoke this mechanism. The electron Yukawa coupling times this extra Yukawa coupling. But ACME 18 ruled us out. So that's why I started this talk saying that how do we remedy that? So you need to change this assumption. But let me show you the apparatus because it brings about the point that Professor Yang Fang Chen will be very happy. Well, not your field. So this is more like AMO, lasers and so on. So let's not read it all, but there's this schematics, okay? 20 centimeters. So the distance that this thorium oxide molecule, cold molecule, drifts is 20 centimeters. Just this, the span of your fingers, okay? And unlike particle physics, this is genuine tabletop. You can see physical PMTs, okay? So, boy, and they are chasing down LHC. And they had the audacity to call the name ACME. I don't know what, people here must have seen this widely called coyote, okay, blowing himself up. So they self-deprecate. Cornell chased this, Eric Cornell. So he got a comparable bound 3 years after the Harvard group, but quickly surpassed, left behind in the dust. So we wrote another paper. We turned on this rho E, this extra electron Yukawa coupling. And we could manage a 2-order magnitude suppression mechanism that is very natural. Okay, let me not explain that. This we're very happy with. We did not fully expect it, but it turned out this way, that the extra Yukawa coupling, these are diagonal elements, ratio behaves the same as in the one that we already know. And we have survival space for barogenesis, so we can explain the splendor in the heavens. Okay, so here, the spectrum, the particles I mentioned, the spectrum are really fit for the LHC, because for LHC is 13, 14 TeV, and this is sub-TeV. TeV is up here, okay? But what makes me put it this way? So let me quickly explain. Okay, now you say horrible. But this is the Higgs potential I've introduced. This part looks exactly the same, just symbol change. So you can do this to engineer the VEV, generate the top, WZ, and Higgs mass. That part is retained. So this minimization condition, let me bypass, and this is not exactly the authoritarian principle. This is the traditional naturalness principle. If I say so I have one scale parameter, VEV. If I say the remaining dimensionless parameters, so all the eta i's, 7 of them, and then this mu1 2 squared is eliminated. This mu2 2 squared, which is a mass, should be positive definite if all of them are order 1. then they are in this ellipse. Okay, why? Because if I go further up, I have to either introduce strong coupling. These are coupling constants, and mu2 squared is a damping factor. So all the nice dynamical effects would damp away if mu2 becomes too large. And if it's too light, you start to worry that, well, we should be able to sense it with the light boson that we have already seen, and we don't, okay? Okay, let me bypass this comment. Okay, this picture I have to show. So we have proposed these processes. The same sign top is due to you have a rho TC coupling here in this production of the scalar boson. And the scalar boson decay, if it's through this TC coupling, you have same sign top. If it goes through this rho TT, you have triple top. So somehow I could not convince our group members to really work on this. So bypass that. Oh, okay, so more work. So fall last year, I hired an experienced hand. His employment with NTU started in February. He's at CERN, and I'm sure you have asked it. He's holding a glass of Montepulciano, okay? So a joke, I asked his permission to use this, okay? I'm a legal person, okay? So he accepted that, and in return I said, when you find good results, I'm going to buy you a good bottle of French, okay? So he's working on that now. No results yet, but worked for a considerable time already. So after that, he'll turn to this. Okay, so there's some astounding effects, but maybe I bypass that. If you want, we can come back. It could be true. The spectrum could look like this. Okay, we have written papers on that, but in the end, I hope I can still spend 1 minute on this slide. I asked a question for you. You see, Glashaw's concern is not unfounded. It's very dangerous with these flavor-changing couplings. So if I say I have sub-TeV scalar, extra scalar, pseudoscalar, and charge Higgs, where are they? I asked this question already. So we have not seen them. So what hides them and what hides their effects, okay? I've already mentioned one, the mass mixing hierarchy, okay? The rho matrix trickles out, becomes smaller as you move more off diagonal, okay? But the surprise is the thing called alignment. Experiment, since the discovery, has found that this H is very, very close to a single Higgs standard model, okay? So what that means is that this mixing is because these are both CP even Higgs, and when you have the same quantum number, two states mix, okay? It says this mixing is very small. Now you understand why I don't want to push this too low, because we already have this guy at 125. It's 200, I can't believe that we don't sense it, okay? Why are they not mixing? It's not natural. So this is a very juicy thing that few people have read and understood, so I'll not try it on you. But this is quantum mechanics. I even use the word level repulsion, words that you're familiar with. If you want, we can come back to this. This is a comment saying that for the experts, KR mixing, B mixing, and BS meson mixing, these are the best probes we have in nature. Yeah, Professor Shong already nods his head, but the corresponding rho matrix just does not provide the thing to be tested. So I find I'm bothered by this. It's very mysterious, but I have to state it. So this is about, I have many things to say here. Oh, this is just to say experimentation is not just Bell and CMS. And you see here a lady, so that gives you the scale. These are superparticle experiments, but not as gigantic as the experiments that we do. So there are many things I can say, but okay, so this page is on what we're not doing here at NTU, muon decays. Very, very nice. Oh, the muon decay, let me comment one thing. I said 1948, Pontecorvo did the first experiment testing mu-T gamma. Wow. 72 years later, people are still at it. But look, so this is the current bound. The current bound is below 10 to the minus 12. Try that, okay? And look at this mu n to En. It's not a better bound currently, but they plan to push down to beyond 10 to the minus 18 in the coming decade. So now you see my point of an error. It's not just our experiments, but other experiments as well. So for B physics, I've been promoting this 2 weeks ago to our Bell group, this process. I think if people have specific questions, I'll just make this last comment that here, the red stars are the standard model. So this G2HD and these arrows, I didn't draw arrows here because they just live by. And here you have quantum interference of the new physics effect with a standard model effect. And this is where the juice is, right? And this is where either CMS or Bell 2 territory. So this is a spot that I'm paying attention to. And so what hides, I asked the question again, why we don't see them. I hope, this point I should make, the red arrows tells you they just live far away. There's a protection mechanism as shown on the previous page. And we are entering a new flavor era, probing here. Maybe we will crack the code. Okay, so let me conclude. So this part, allow me to read. Since the Higgs discovery, we saw no new physics at OHC. So hybrid physics seems rudderless. For the students, rudder 是舵，失了方向盘啊。Or put it another way, too many rudders. 大家都在掌舵啊，太多方向 too many engines, too many drivers. Okay, we're moving or not moving, depends on your perspective. Whereas, I think the most likely new physics is actually in plain sight, but we just don't look for it. Okay, and this is the second Higgs doublet. We said it can touch the heavens, barogenesis. It can touch the Earth. It can, if Gabriel sees sees a electron EDM, a value rather than just a bound, I think the model so far can account for it. Okay, so Godspeed their success. So we have illustrated that these are sub-TeV extrascalar bosons. Their effects have been well hidden from our view, really well hidden, because of flavor structure. We did not expect the flavor structure. Alignment. Nobody predicted this small HH mixing that suppresses the small h to have these couplings. So although I very quickly skimmed over them, we have proposed direct search modes and also indirect probes. So the mission is now clear. Find the buggers and crack the flavor code, okay? And at this university, we are in CMS and Bell 2, so we have access to them. In fact, this Barcelona FC means flavor change. No, but you know what FC means, right? So in a computing experiment, Barcelona FC has also started. They contacted the theory side of this effort. So I'm serious about this. It's a mission because I think it's highly probable that this thing is true. If not, we still have to probe. Okay, thank you very much.
Okay, now the floor is open for questions. Okay. 在后面最后面。
Can I ask in Chinese or? Also, can you go back to the slide 24, page 24?
24.
I guess.
Okay, let me first get out and not 24. This one.
Yeah, I have questions because I'm not familiar with particle physics. What's the meaning of the right panel, the plot? What is that?
This is the phase of this rho tt, and this is the strength of this rho tt. Okay, so this BAU says that it's equal to 1 for the black curve. So right-hand side of the black curve are the allowed parameter space. So yes, I went through it very quickly. The thing is, this r equal to 0 living here is ruled out by this gray area. That's the ACME 18 result. So we made a simplifying assumption by assuming rho e to be 0. Okay? But by putting rho e back in, we find we can still have barogenesis and account for electron EDM as low as below 10 to the minus 30. Okay. Actually, I think in my talk I said I don't think this region is ruled out. 10 to the minus 29, only one experiment. So I don't know. Our AMO Institute should do it. Challenge them. Okay. It's a great achievement if one does it. So I think 10 to the minus 29 is still open game. I think Eric Cornell knows that, okay? Who says, how smart Gabriel's is, he can still make a mistake. His student can make a mistake, okay? But the thing I bring out to you, though, is that electron EDM is a forerunner now, a front runner about science, on probing CP violation. It's staggering. Okay?
Thank you.
You mentioned there's one channel that was not pursued, that is not pursued by the NTU team. Is that the same charge, the top quark pair?
The top up pair that I did not mention.
You mentioned that the NTU team will not pursue those channels.
No. Our group member, the problem with the modern HEP, this is the difference between also Bell and CMS. CMS analysis, once you invest in it, it takes 2 to 3 years just to finish. Bell is much easier. So our manpower has been invested. So I've been saying these things for the last 2-3 years. Nobody has started working on it. So that's why I went out and hired someone to start doing it. So NTU is doing it. So HEP is doing it. But the group manpower has been tied up. Okay. So I'm not saying they're bad guys, etc. But Barcelona people are pursuing it, so at least someone is taking notice.
What is the Goldstone boson, the mass of Goldstone comes
0.
from?
Goldstone boson, by definition, has 0 mass.
But
Okay.
Goldstone prime and Goldstone 0. What is the mass come from?
It's a mathematical theorem of field theory. So the Goldstone theorem, rigorously proven, is that if you have a continuous symmetry that's spontaneously broken, then corresponding to every single generator of that continuous symmetry, there will be a Goldstone boson that is massless. That is sort of the remnant of the symmetry. Actually, the symmetry is spontaneously broken, but in a sense, not broken. So the masslessness.
That's the Goldstone theorem, right?
Goldstone theorem, yeah. It's Goldstone Salam Weinberg theorem.
How to prove the Goldstone theorem is very difficult.
It was not easy. So that's why I say the true Goldstone theorem is not Goldstone by himself, but it's Goldstone, Salam, Weinberg. So I'm in Weinberg.
One
Nobel
breaking, one Goldstone.
Huh?
One breaking, one Goldstone bomb, right?
What?
One broken symmetry, right? Generate one boson, one Goldstone.
Yeah. Every continuous symmetry that's spontaneously broken will have a Goldstone boson, a massless particle.
This theorem is saying.
Yeah, but the thing is, we basically don't see Goldstone bosons in nature. Somehow they always.
Sometimes you can explain the proof of the Goldstone theorem. Very difficult to understand.
Well, I only used. I did not feel I need to mention Goldstone's theorem. It's just saying that the Higgs mechanism, the Goldstone is removed. In fact. Okay.
So anyone? Anyone else?
Hi, Professor. Professor Ho, thank you for a nice talk. And I think this is an extraordinary speech because yesterday was Annie's birthday and today is Zhening Yang's birthday in ROC passport. I have just a quick question. As you say, the Meissner effect means the electrode has a damping behavior. Has a damping behavior in superconductor, right? Is this related to the complex charge you just mentioned, or
what charge? No.
Complex charge?
Meissner effect is really just when the photon is propagating, so the magnetic field is trying to penetrate the superconductor. But currents will be generated. It's superconductivity, so the current is at no cost. So you'll generate plasmons, or the photon becomes a plasmon that is effectively massive. Okay, but mass transforms to a length, and that attenuation length is related to the massiveness of the photon. I don't work on condensed matter. I did look into London theory. It did not assume all of this. It's done differently. But Phil Anderson was the one who claimed, therefore, to invent the Anderson mechanism, which we call the Higgs mechanism. Okay? So that mass generation of a massless gauge boson coming from this symmetry breaking. Okay?
Oh, yes, okay.
It's about condensation. Yeah.
Oh, okay, thank you.
Anyone? Okay, so the Professor Holder introduced some of the ideas that we can probe. Nowadays, in the particle physics world, now we found whatever all the standard model particles, but we know the world is not like that. It's something we still don't understand. So that's what the current situation in the our field, high energy physics. So, but we have participated in the CCMS and the Bell2. It's a world-leading experiments in the world. So there's a lot of research opportunities and a lot of search that we can explore. So if you have interest and want to join us, please come to our office. All right. If there's no other questions, let's thank Professor Ho.
Thank you.
I had one last slide to thank you. But I hope you see the metaphor. A Higgs, A second Higgs.
It means if we find a second Higgs, we'll probably get the Nobel Prize. Really?